And welcome back to 3.1 podcast. In the last podcast, we were talking about scientific notation, the fact that you're going to put the decimal after the first non-zero number and then express the number of places you need to move the decimal as a power of 10. And in this podcast, we're going to start off by taking the scientific notation back to ordinary notation. So we are now in example number 2, letter A. If the speed of light is 2.9979 times 10 to the 8th power, how do we express that in ordinary notation? Well, again, what you're trying to do is you're going to move the decimal back to where it should be. So if I write these numbers out, 29979, currently, it looks like we're in right here. We switched to orange. There we go. We're back to orange. The decimal in the scientific notation is here. We need to move it 8 places to the right because it's a positive number. So that's going to mean we're going to need to move it 1, 2, 3, 4. Now we've run out of digits to pass the decimal over, so we have to start adding zeros. So once again, 1, 2, 3, 4, 5, 6, 7, 8. 5, 6, 7, 8. So the decimal would go there. And so what we have is 29979 with 4 zeros past it. So what we have is 299,790,000 meters per second if we were going to be adding our units in there. Right now we're only concerned about the numbers. If we were actually reporting this number in a lab report or as an answer, we would obviously need to have the unit. All right, the next one is what's called the Boltzmann constant in joules per Kelvin, whatever that means. We'll get into that later on in the course. But here's the number, 1.380 times 10 to the negative 23rd. So once again, what I would do is I would start off by writing the number down, 1380. The decimal is right here currently, and we need to move it 23 spaces to the left because it's a negative. So we have 1, and then once again we're going to have to start adding zeros. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. The decimal would be placed there. And we'll throw one more zero in after the fact. So what you essentially have is 22 zeros past the decimal plus jumping over the 1. So the final number would look something like this. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 1, 3, 8, 0. That is a very small number. Here's another thing in terms of scientific notation. Another advantage to scientific notation is not only not having to write out all these digits, but number 2, it's easier to compare different numbers. For example, a number which would be 100 times larger than this Boltzmann constant would look something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 3, 8, 0. Now, if you're comparing these two numbers and they are relatively far away, you might not realize how big this number is compared to this number. But if you know that you have there we go, 1.380 times 10 to the negative 23rd compared to, in this case, 1.380 times 10 to the negative 21, you can see that this number is going to be the bigger number, and it's actually 100 times bigger. So it's easier to compare numbers that are very, very large or very, very small. All right, letter C. We have 7.00 times 10 to the negative 7, which happens to be the wavelength of red light in meters. And so once again, we're going to write out our number and then move the decimal. It has to move 7 places to the left because it's a negative number. So we have 1, 2, 3, 4, 5, 6, 7. The decimal would be placed there. So our number is 0.1234567, and then I can put the other zeros behind that. So that is how you move back and forth between regular notation and scientific notation. Let's double check on the time here. Looks like we have some additional time before the 10-minute is allotted is up. So let's go down and have our discussion on the differences between accuracy, precision, and error. When you take measurements, there is an inherent inaccuracy in this, but some people don't understand what the term accuracy means versus precision. All right, so let's look at these diagrams. In this first one, letter A, we have what's called good accuracy and good precision, where all the darts are hitting the target. In this second one, we have poor accuracy. Letter B is poor accuracy. Why? Well, because the target is the bullseye, and they're nowhere even close to the bullseye. So those darts are not very accurate. However, you have good precision. What does that mean? Good precision means that you're going to be able to repeat your results over and over. So it doesn't have anything to do with how close to your target that you are. It has to do with how close each individual measurement, or in this case, dart throw, is to one another. And then in letter C here, we have poor accuracy and poor precision because none of them are near the bullseye, and really none of them have repeated one another. They are not even close to each other. So, just so you know, accuracy deals with how close, or the closeness to the target or actual value, where precision deals with the closeness of each measurement. Okay? It has nothing to do with how close it is to the actual value. And then error, you probably already know, is how far from the actual value you really are. So we'll just go ahead and write that in. How far measurements are from the actual value. Alright, so that's the difference between accuracy and precision, and then of course error is thrown in there as well. As we scroll down to the next page, here's some some equations for you to think about. Error is simply the experimental value. This is what is measured, minus the accepted value, or we're going to say that's the real value, but in reality there's a lot of values that don't have a real value. We don't know exactly what they are. We can only measure them and take measurements on them over and over again. But the error is the actual distance from the real accepted value. The percent error expresses that as a percentage. Now, why would you want to know the difference between those? Well, let's take a look at if we're measuring the speed of light. The accepted value of the speed of light is 299,790,000 meters per second. That's the actual value or the accepted value of the speed of light. Let's just say we made a measurement that was 299,690,000 meters per second. All right. When you subtract those two, you are actually off by a whole million meters per second. So that your error is your error is 1 million meters per second, not 100 million. It's 1 million meters per second. Is that bad error? Well, not when you consider the fact that these are very, very large values. 1 million meters per second is actually fairly close to, or the difference of 1 million meters per second is actually fairly close to the accepted value. The percent error is the absolute value there. Now, if you remember, absolute values is simply taking your real value and making sure that it's a positive number. If you take your error, which is 1 million, and divide that by the actual value, which is 299 million. Oops, got the decimal in the wrong place there. 790,000. You have a value that's going to be less than 1% error. You're actually very accurate. Okay, we're approaching the 9 minutes. We'll get back in just a second.